Water is usually thought of as a gentle, life-sustaining liquid, but in chemistry, it acts as a harsh baseline, an aggressive stress test used to expose the hidden traits of solid metals. When these two forces meet, the baseline reaction is straightforward. A solid metal reacts with liquid water to yield a metal oxide and hydrogen gas. This flowchart maps out the two-step sequence. First, the metal and water combine into that initial metal oxide. Then, if that oxide is soluble, it absorbs further into the water, transforming completely into a metal hydroxide. But this process is highly inconsistent. Some elements violently complete both steps in freezing conditions, while others stall out at the very first step, even when the water is boiling. By systematically escalating the thermal energy of the water, moving from cold to hot and finally to gaseous steam, we can map out a strict hierarchy of chemical aggression. We start with type 1 metals, specifically potassium and sodium. These elements require absolutely zero external heat. The moment they touch cold water, they trigger an explosive reaction. Looking at the textbook equations here, we see potassium and sodium reacting with liquid water to form potassium hydroxide and sodium hydroxide. Notice the end of the equations. They release so much heat energy that the newly freed hydrogen gas instantly catches fire. Moving down the text to calcium, we see a slightly different outcome under the same cold conditions. The reaction still forms a hydroxide, but the heat generated isn't enough to ignite the hydrogen. Instead, the hydrogen bubbles stick to the metal's surface, causing the solid calcium to float. These highly electropositive elements carry enough intrinsic energy to violently force the creation of stable hydroxides without drawing a single degree of thermal assistance from their environment. Magnesium, a type 2 metal, lacks that immediate aggressive energy. Submerge a strip of magnesium in cold water, and it remains completely inert. To force a reaction, we have to inject energy. Heating the water crosses the required activation barrier. Once hot, the magnesium reacts, forming magnesium hydroxide, and begins floating as hydrogen bubbles cling to it. We can prove this chemical change visually. By adding a phenolphthalein indicator to the mixture, the water turns bright pink, confirming that a basic solution, the metal hydroxide, has been created. For these mid-tier elements, external thermal energy must be injected into the system to overcome their natural chemical resistance. Type 3 metals, aluminum, zinc, and iron, require water in its absolute highest energy state to react at all, gaseous steam. But here we encounter an anomaly. Unlike the lower tiers, when these metals react with steam, they produce metal oxides, not hydroxides. This animation illustrates the thermodynamic mechanism at play, heat-driven decomposition. The intense temperatures required to make steam actively destabilize the bonds of a hydroxide molecule. It literally vibrates apart, releasing water and leaving a raw metal oxide behind. As the scale tilts, the increased entropy of generating steam heavily favors the formation of the oxide. The thermal energy simply blocks the hydroxide state from existing. This excerpt from the textbook provides the exact chemical proof. Looking at the aluminum and iron equations at the bottom, the reactant is explicitly labeled as gaseous water, H2O, and the resulting products are solid aluminum oxide and iron oxide. Finally, type 4 metals, lead, copper, silver, and gold, possess an absolute immunity. They refuse to react with cold water, hot water, or even superheated steam. The final molecular product of any metal-water reaction is a constant tug-of-war between the metal's innate reactivity and the destructive thermal energy required to force the change. By stepping back from the isolated chemical reactions, we can organize all of this temperature data into a single structured hierarchy. This chart illustrates the reactivity series. At the very peak are the violently reactive cold water combustors. In the center sit the thermally dependent mid-tiers, and anchored at the base are the completely inert precious metals. This invisible hierarchy governs the physical world around us. It dictates exactly which metals will corrode instantly upon exposure to the elements, and which can sit at the bottom of an ocean fully intact for millennia. The reactivity series serves as a precise map of the exact thermal energy required to force nature to change its physical state.